This session this morning is about real catalysis, how to make all these samples and all the fine art involved in making those things, and we get some insights from various groups, how they look in various aspects of the surface, of the catalyst species, what's going on there, and I hope it's enlightening to all of us to learn a little bit more and take something home to get inspired for their own work. We will open with a keynote lecture from Exxon. Stu Solid will present on hydroprocessing, nickel phosphides, as I remember right. He will come on stage too, but before we introduce him in a little more detail, come on, you don't need to run away. His co-chair here is Gerhard Mestel from Clarion, former Südchemie. Maybe he also wants to have a short few welcome words, please.
Maybe there is another important message to you guys. Please remember to switch off all your cell phones. It is really not very pleasant if these things start to ring. Thank you so much, and have a nice morning session.
So Stu, now it's on you, and get us inspired, get us some insight in the work you've done, and as all of us, I hope we all have a nice take-home message. Please.
Thank you. Okay, thank you very much for the introduction. I'm very happy to be here, surrounded by a sea of bourbon, horse racing, and tobacco. So it's a perfect background for my presentation. So I'm gonna raise a question at the beginning of my talk, which is right there. Can nickel phosphides become viable hydroprocessing catalysts? And if I succeed at the end of this, actually rather short study, I hope to come to a conclusion. And well, you'll let me know if I did, and certainly be open for questions after. So I just wanted to indicate my co-workers, Sal and Joe, have worked with me for about 30 years each. We're still hanging in there. And Javier is just a few years with ExxonMobil and has helped with this work. We also had, and you'll see a little bit of work from Argonne National Labs, from Trudy Boland. This is not Argonne National Labs. This is the ExxonMobil research site. And these are geese, not algae in the pond back there. So, okay. So why, for someone like myself that's always loved to try to make things and get into the catalytic materials part of the world, and working in the area of hydroprocessing, one thing sort of strikes you very early on. And that is that if you want to work on things other than moly and tungsten sulfides promoted with nickel and cobalt, there's not a lot to work on. So sometimes it gets boring. You feel like, okay, we have a pretty big periodic table, but we're stuck in one spot. And of course, that spot has been worked for multiple decades. And the interesting part is that there's still new things coming out all the time, which is pretty amazing and speaks highly to the fascination of catalysis and catalytic materials. But sometimes you get the feeling, maybe I want to expand past that. And so every time something comes up in the literature or someone presents about a different type of hydroprocessing catalyst, it catches your attention. And that's what happened with nickel phosphide. There's a lot of work going on in that area. I'm hoping this small contribution at least raises some questions and points to a direction that maybe we can think about further going into. So, but let me just go a little bit further into background. Okay, this is supposed to work. Okay, Maestro. It worked for one click. There we go. Okay. So other than nickel phosphide, I think when I first started to see what other things might be interesting, there was a lot of work actually at ExxonMobil before I got into the area, done by Russ Chianelli, June Passeretti, and others, about ruthenium sulfide. And ruthenium sulfide was reported to be a very active catalyst, and then they actually had some catalytic data that showed it was quite active. Now there are issues with ruthenium sulfide because the world supply of ruthenium is a little bit constrained. in the sense that if you fill up one reactor with a ruthenium sulfide bulk catalyst, which is what they were working with at the time, you would probably exhaust the annual supply of ruthenium sulfide. So it had an issue, but it was kind of interesting, and of course it was very expensive. But what it turned out, let me see, I guess I have to use these things. Yes, was that the ruthenium sulfide was really active only when you had a, did you press that? I'd rather you give me one that works. I'll do this, okay? Thank you. So it only really worked if you had a very highly loaded or bulk ruthenium sulfide sample. And it suggests, therefore, that the site activity, it's a structure-sensitive catalyst and reaction over it, but kind of in the inverse way that sometimes we used to, in that it worked well for large sizes and not for small. And that's not unprecedented. I've seen that very recently in a presentation on platinum oxidation catalysts, where large platinum worked very well, small platinum didn't. And I think it's a common feature between the two, in that when you have small particles, particularly of metals, they tend to either oxidize or sulfide very easily. So it turns out it's not really ruthenium sulfide that's so active, it's actually patches of ruthenium metal. So if you make very small ruthenium sulfide crystallites, which we have done, they don't work at all. So this makes ruthenium sulfide probably not a very good candidate. Okay, so on getting back to nickel phosphide then, there was a lot of work probably about in the last 10 to 15 years. This all seemed to have started with Ted Oyama's group at Virginia Polytech. There were a whole bunch of papers and initial work from him on nickel phosphide and nickel phosphide being active. They did a lot of work trying to identify, or at least normalize the activity at first towards the number of active sites using CO as a titrant. Later on, there were some claims that the catalyst was as active as commercial catalysts. Well, what actually the people that work in the area, in the various companies that make hydroprocessing catalysts, nobody has moved forward with that. And the reason to date has been that so far those first embodiments were not anywhere near as active as the conventional catalysts. But there's still, that's just, version number 1. Most of these other catalysts are in their version number 15. So is there something that can be done with that? And so the question comes up, what else can we do? And so yes, in Ted's original preparation route, which involved reducing nickel phosphates at relatively high temperatures, 550 C, that in itself sort of alerts you to an issue. When you do reduction at that high a temperature and make an active species, it's quite likely you're going to wind up with problems of sintering. And you're going to see, and I'll go through some of the data as we go through the presentation. It turns out that, yeah, those catalysts have very low surface areas. It's very unusual that you could think that they would be as active as Moly sulfide crystallites that are in the order of 3 or 4 nanometers. You have something order of magnitude larger at least. So the question remains then, yes. So then they moved, the work moved ahead with making nickel phosphate precursors, as you might often do, put it on a support, try to get the surface area a little bit larger. And so there was some work with translating that into silica, carbon, a little bit of improvement, but not a major change, I would say. So in the end, Ted's work stimulated a lot of continuing interest, and as we see, still leaves us the question, can nickel phosphides become viable hydroprocessing catalysts? I don't know why this doesn't work. Okay, so here's essentially the reason. Now, I only have one pointer, so I was going to try to do something like this if I had 2 of them, but I'm only going to be able to point here, but you can see the same thing on this side, hopefully. Yeah, this is the problem with the reduction of nickel phosphate. So here's what happens when you take nickel phosphate and you just heat it up in hydrogen. This is just a simple TGA, but it really shows you the whole problem. You had some water loss at low temperature, but basically the reduction onset begins at about 500 degrees C. And this is the conversion to the phosphide over here. So you have to generally hold this at about 550 degrees C for several hours to get to the phosphide. That's, as we mentioned earlier, that's a big part of the problem because you wind up with low surface area materials when you do that. And generally things less than 5 meters squared per gram. This will work if I raise my hand? So then he'll see me. Okay. How high? This high or this high? Yeah. Okay, hi. I never quite had this situation before. Okay, so now we get into, and unfortunately I have a lot of animation in this talk of all things. So what are the possible alternative approaches that one could try to move forward with in this area? And that's what I'm going to try to outline now. So here are the things we would like. First of all, and working in industry, this comes on clear very early on. You get hit in the face with a number of things, one of which is whatever you're going to try to do, it needs to be environmentally acceptable. So whereas we might, and we'll see there is some work of people using phosphine gas to try to make phosphides, it's probably not something you're going to do on a multi-ton scale. So things should be environmentally acceptable. And oftentimes in hydroprocessing, what we wind up doing is working with stacked beds. So you might have catalyst A, catalyst B, catalyst C. And that's done for a variety of reasons, sometimes economic, sometimes just for certain process reasons. So classically, the sulfide catalyst is most of the time is sulfided in situ in the reactor. You start off with precursors. They are treated with a sulfiding source, usually dimethyl disulfide, and that converts it in situ to the sulfide. So now if you're going to think of using a phosphide catalyst, it would be nice, not absolutely necessary, it's not a requirement, but it would be nice if you could create the sulfide, you could create the phosphide under sulfiding conditions. Now that sounds a little strange, but we're going to show you, and that's one of the bottom lines that we have from this study, is that you can do that if you set them up in a certain way. Okay? Now, as we mentioned before, the problem we've seen here is that the precursors are a fairly low surface area, the reduction temperature is too high. We need to work on both of those things. So we need to start with making higher surface area precursors, and we need to be able to do the reductions, if we're going to do it from a reduction mechanism, at lower temperatures. Okay, so those are all kinds of things that you would like. So you say, first off then, what if I use a normal reduction promoter? And people use this oftentimes with mixed metal oxides and supported mixed metal oxides and so on. You put in something that can dissociate hydrogen or whatever the species is that's going to do the reduction. In this case, we're doing the sulfidation. So you would like to be able to do, when you put platinum in a sample, yes, the platinum can dissociate hydrogen at lower temperatures, and then I know the word spillover has become a little more controversial the last year or two, but let's just use it loosely, that the hydrogen can spill over and reduce an oxide phase, which is much more difficult to reduce in the absence of the dissociated hydrogen. So what about doing the same thing here? How about we put some platinum on this catalyst? Well, the problem with platinum is that it's poisoned by H2S. So platinum's not a good choice, but getting to be able to reduce hydrogen at lower temperatures in the presence of H2S is part of the goal of what we have. And so the bottom line is what we're going to try to find then is a promoter that dissociates hydrogen in the presence of H2S, and we're going to try to start with higher surface area precursors than in the conventional precipitated phosphates. So that's the goal that we started out with. And if we continue on, so let's review some of the approaches. Now, from the time that Ted's work came out until now, there's been a lot of work done in the literature, and a lot of very nice work. There have been some groups, Mark Bussel's group out west in Washington has worked on this for more than 10 years. Roel Prins is started to work on this, so there's some pretty good stuff out there. And I just want to review a little bit about what some of these approaches are. So, as we just mentioned earlier, the first one was the reduction of the phosphates, whether they be bulk or supported. The use of phosphine. So Roll, who I have an immense amount of respect for, has worked that issue, trying to take precursors and treat them in phosphine and hydrogen and make the phosphides that way. So let's keep going. Now, people have thought that maybe one of the issues here is that the phosphorus-oxygen bonds in the phosphate are very strong and hard to break. So instead of working with phosphate precursors, what about things like phosphides or hypophosphites? So the phosphides have phosphorus in the +3 state. The hypophosphites have phosphorus in the +1 state. And so there's been some work in that area, and actually it is related to what I'm going to talk about today. So let's keep going. There's been a lot of work on nanoparticle synthesis, and you're going to see when I get to the end. I kind of like that, but I like it in the context of proof of principle experiments, and I think some more of those are very good. So that has actually helped this area in the sense that you can make smaller crystallites of the nickel phosphide using that. And people have also looked at other compositions, not just nickel phosphide, but making mixed metal phosphides and even noble metal phosphides. Okay, and a very nice review paper on this whole area, which if you're really interested in it, and I think some of you in the audience do work in this, and you're probably aware of this, is Roll's and Mark's review article from about a year or so ago, where they talk about essentially the history and the possible directions. Okay, so what we're going to talk about specifically today is making phases that are somewhat related to things I've talked about above. We're going to actually talk about making hydroxyphosphites, nickel hydroxyphosphate, phosphide precursors. We're going to show you how they're made. We'll talk a little bit about the structure. We're also going to show that we can actually substitute a little bit of molybdenum into the hydroxyphosphide. And the consequence of that is very interesting, because when you treat that now in a sulfiding environment, some of the molybdenum pops out of the structure, forms MOS2, and MOS2 is able to dissociate the hydrogen in the presence of H2S. And that enables you to do the reduction at lower temperatures. So you have an interesting synergy by putting the moly in there, and we're going to see there's another effect of putting the moly into the structure. So how did we get into this? And it's just, and that's what I'm going to talk about next. So let's go on to the next one, please. Okay, so it actually came out of kind of doing exploratory synthesis, which is something that we do a lot in our labs. We were working with the system with nickel and phosphorus and moly, and we found, actually, that we intersected in our work, and I'll show you how we made them in a minute, some prior work that was done actually in the early 90s by Professor Atfield's group. And he actually delineated these phases, yes, of this hydroxyphosphite phase, where the M here can be many of the divalent cations, zinc, cobalt, nickel. And he also talked about, interestingly, that at least some of the phosphorus could be replaced by vanadium or tellurium. And this is a picture of an X-ray pattern of a phase that we've made. Actually, it's the same as what he reported. So that was where, doing the experimental synthesis, we intersected this particular compound. And we thought this was quite interesting. So if we go on to the next one. So here's how we actually wind up making them. It's very simple, and this is consistent with the idea of make something simple, at least in our world, make something simple, scalable, and not usually expensive. And then so you can see here, and let's go on. It's a hydrothermal preparation. We did see a partial substitution of moly for the phosphorus. Now, as I mentioned on the last slide, he talked about replacing some of the moly with vanadium and tellurium. We found that you could actually put moly in there, which was, well, he hadn't reported that, but it works very nicely. And if we go on, and all we have to do now, it's a very simple reaction. You just react nickel carbonate, molybdenum oxide, phosphoric acid, put it in water, put it in an autoclave, 200 degrees, and hold it overnight. Very simple reaction, and when you do that, you wind up with that particular structure that we showed on the last one. And in this very simple study I'm going to talk about today, we're going to just look at essentially 4 samples to start with. And these are different nickel, moly, phosphorus nominal ratios Now, what we saw early on very clearly is that when we put the moly in the reaction mix, most of it doesn't wind up in the solid. It just winds up not going anywhere. A small amount winds up replacing some of the phosphorus. So you don't get a total substitution. You get a partial substitution. The more you put in the series at the sample number 1 with the higher nominal moly content, you get more in your solid. As you go down, you get less. And to the extent that we get about 10 to 20% of the moly that's present in the reaction mix in the solid. Okay, so what are the consequences of that, and why have we been able to take advantage of it? So if we go on to the next one. So here I'm actually showing you the crystal structure that the Atfield group reported, and it's kind of an interesting structure, and you can show the next little thing. So it's a tubular framework. The phosphites, these purple guys over here, and there's 3 oxygen coordination. The hydrogen points into the center. They're over there. They're also in these other tubes down here. But one of the things you can see about this is that the structure has a lot of, the coordination of the phosphite, it's got a lot of empty space in there. So it's able to adapt and substitute things of slightly different size and geometry. And I think that's the reason why you can easily replace it with a number of other species. So it was a very accommodable structure, which is something we always like to find. And if we continue on, please. Yeah. So as we said, then just to summarize, the anionic phosphite groups are located inside the channels, and they're in a tetrahedral environment. Actually, it doesn't help if I point down here, right? So these are in tetrahedral environment. And in addition to the species that they reported, we were able to get molybdate in there. So let's look at some of those materials now. Okay, so here, this is interesting because this is the nickel, this is the nickel hydroxy phosphite, the bottom one here, the dark red one. No moly in here. This is just a neat phase. So if you take this phase and you heat it up to, say, a sulfiding temperature, 400 degrees C, and hydrogen H2S, basically nothing happens. It just looks at you. So that's not good. We would like some action to happen. So now if we take the one that has the moly substituted into it, which is on the next one, yep, so that's the blue one. And we'll see in more detail that actually this precursor, the peaks are broadened, and we'll talk about that more. But the most interesting thing is when we subject this to a 400-degree hydrogen H2S treatment, we wind up with a very simple pattern that looks like this. And if you look down here with the corresponding X-ray pattern of the known phases, it's Ni2P, essentially quantitatively formed. And that only happened when we had the moly there. And the reason for that is this. We have a little bit of the moly that was in the phase came out and formed a little bit of MOS2. So this is our species that's doing the hydrogen dissociation and doing the reduction of the hydroxyphosphite to the nickel phosphide. Okay, so let's go on to the next one. What was unanticipated and also kind of interesting here is when we put the moly into the structure, you can see as you compare the red one on the bottom to the green one slightly above it, these are the nominal amounts and we're going up as we go up on the graph. You can see the X-ray pattern is essentially the same, except the peaks have broadened. So putting the moly in there has seemed to increase the surface area of the material, and you can see I have the surface areas, the measured surface areas. So they've gone up from about 15 on the starting phase to about 50 on the phases where we have the moly substituted in there. So that's in the right direction. It's not quite as far as you'd like to go, but it has allowed you to access higher surface area precursors. Now, we would like another factor of 5 or 6 in that, but that's as far as it went with being able to do this. And as I indicate on the bottom, when we went and did chemical analysis of the solids, when we started out with the nominal stoichiometry of the top one, the high one where the moly was put in there almost at the same level as nickel, we have about a 7-to-1 nickel to moly ratio. So only a small amount of the moly winds up in there. Now when you take each of these and you go ahead and you sulfide them, because that was our goal all along, to be able to do this in a sulfide environment, you'll see what we get on the next slide. Well, actually, first, I just do a comparison over here between the BET measured surface area and what we get from particle size broadening measurements from here. And it's a pretty decent agreement, so we're pretty confident that those are correct. And go on to the next slide, please. So now you see what happens with those three phases when you heat them in H2S hydrogen. So on the bottom one, again, no moly in there, nothing happens. If you look at the three with the moly, starting with the highest level of moly, and here we see the MOS2. You can see it more on the top one, the lower moly. You can barely see it here. You don't see much of it. You see Ni2P. You can see the peaks are broadened slightly. The surface areas are now into the mid-50s and 60s. Again, it's going in the direction we want to go, not quite as far as we'd like. And it's interesting, when you have a smaller amount of moly in there, we actually made the Ni12 P5 phase, which is a slight variation. If we have time at the end, we can look at the difference in the crystal structures of the two. Not very different, just slightly. And so you can make either Ni2P or Ni12 P5. And if you have a very, very small amount of moly in there, it looks like a polycrystalline version of the Ni12 P5. So in all cases, though, we're getting higher surface area. We're getting the conversion at lower temperatures than we could working with just hydrogen. And we're able to do it in a sulfiding environment. So all of that is in the right direction. Okay, and so I said before, well, what if you just treat things and, add platinum? So we just did an experiment. This is not what we want to do, because the platinum, in the presence of sulfur, platinum is not active in doing this. But in the absence of just hydrogen, here you can really see a difference in the peaks that you get. So if you take the hydroxyphosphite and reduce it in hydrogen with some platinum on it, yeah, you make the nickel phosphide phase. But you see how sharp the peaks are, and you get surface areas around 15 or so on that, rather than the 45 to 50 that you get if you have the moly around and you do the treatment in H2S hydrogen. Okay, so we had some samples. We weren't sure where we were at, so we decided it was probably a good point in time to do some testing. Now, one of the things you always have to be careful of, and it's very relevant in some of the recent papers that Mark Bussell has published on, what happens in your unit? You put in phases of a particular type, what does it come out? Do things change? It's particularly an issue, I think, with nanoparticle synthesis, whether you can retain the same small particles that you have after you go through the reaction. So let's take a look. I think on the next slide we have, I'm sorry, before I get to that, these are the actual three materials that we chose to do our reaction test on. So we took some of the material without the moly, we pre-reduced it ex situ of the reactor, and then we used that, we put that into our reactor. So there's our platinum one, that's about a 15 meters squared per gram. And we had then our sulfided ones. Now these we actually loaded as oxide, did the sulfiding in the DMDS mixture. But these were the two phases. One, we tried to put in a very small amount of cobalt. In essence, you're going to see, I don't think that's determining anything very much. Other than that, did give us a lower surface area of the phosphide than the one that we had when we made a little larger batch. We round up with 45, 30, and about 14 meters squared per gram. And again, the line broadening and the BT agreed fairly well with each other. So these were the samples that we chose to do the reaction test on. And as I was saying prior to this slide interrupting my last thought, we get careful to look at what happened after the reaction, and we'll see that on the next one. Yeah, so we looked at each of them. This is the one with the higher level of moly, both as we put it in and as we took it out. The one with the slight amount of cobalt in there, that's a little sharper. And then the one where it's pre-reduced with phosphorus, you can see these peaks are much sharper. So things stayed essentially as they went in. We didn't have a massive change or restructuring that went on after the run. So we felt pretty reasonable that what we were measuring was reflecting from what we had put in there. So now if we look at the data, so here's the data, and I plotted this now as the rate constant for the HDS. This is a real feed run, so for those of you familiar with some of the feeds and things that we work with, this is a straight run gas oil. It has about 1.8% sulfur, 160 part per million nitrogen. That's on the basis of most things we work on, a relatively easy to convert feed. The run is done at 650 pounds. Its temperature is 338 C. So it's a fairly straightforward feed. that's often converted into diesel. So if you look at the results, actually what they tend to correlate with very nicely is the surface area of the phosphide phase. So here we have the sample with no moly, the one with the 30 meters squared per gram, and the one with about the 45 meters squared per gram. Now, I know it's only 3 samples. It's a nice correlation. And so what is that trying to tell us? And that's where we went to do the extrapolation next. So if we go on to the next one, what I've done now is, again, expand the scale. So here are the 3 catalysts. I've expanded the surface area and the rate constant scale. And we show next, just do an extrapolation. And so here's a point of, this point is actually a cobalt moly catalyst. So now you see the part of the issue on why all the catalyst vendor companies are not running to make nickel phosphide catalysts. So that's coming up with an activity around 5 on this scale. And now if you extrapolate that over to the surface area plot, and again, yeah. So now we're saying that this is now saying that in order to get to this activity, assuming, and this is a big assumption and something that still needs to be proved and part of the remaining work, I think, assuming that there's no structure sensitivity going on here, it would suggest that you need to make these nickel phosphide catalysts about 400 or so meters squared per gram to get them to be competitive with cobalt moly. Okay, and so if we go on and look at the next one. So here's a plot of what that means. So we just took a simple model of what the lateral dimension of nickel phosphide would be for what its specific surface area would be, and then we put that point on here at about 400 meters squared per gram, and we read down here and it says, okay, you could get something comparative if you're around 30 angstroms or so for the nickel phosphide. So what does that mean? Well, actually, that's about the size of the moly sulfide crystallites that are used in most of the catalysts that are interesting. So it seems reasonable, but it's also saying we have a long way to go in order to get there from version 1 of the catalyst to maybe this is version whatever, 1A, a little bit higher surface area. We still have a long way to go in order to get things down to this kind of surface area. And I'll talk more about that as I conclude in a few seconds. So let's continue on now. And yeah, so basically I say not very different than the active sulfide catalyst. And you probably wouldn't expect it to be. Actually, if you look at what you'd expect the surface of the nickel phosphide to be, it's even more difficult to visualize the sort of coordinatively unsaturated sites that you would have on that relative to those you can create on sulfides and oxides. So I'm not surprised that the number is coming out that small, and it's certainly pointing in the direction that I think we need to all go if we're going to consider these. Okay, so let's go on. So we had some questions about, because we have a complicated mixture there with the nickel, moly, phosphorus, the separation of the phases, do we have some co-mixing of the moly into the nickel phosphide phase? There's even a question of whether we have a little bit of nickel in the moly sulfide phase. So we haven't addressed all of them. We did a little bit of work, thanks to Trudy at Argonne. We looked at some near-edge spectra that she helped us with. And I'm going to show you some of that data now. So let's just go through that quickly. This is the phosphorus edge, and she compared it against a titanium phosphate material or titanium phosphide material. And you can see that actually this red spectra, which is the sulfided, has the same type of edge spectra that you get from the phosphorus edge once we do the sulfiding here. So again, probably consistent. I'm pretty sure that the phases we reported are the ones that we have, but let's go on to the next one. So here we look at the nickel edge, and this is a nice reference spectra for nickel phosphide, and that essentially has the same features that we have on the nickel edge. So that corresponds very nicely to actually making nickel phosphide. What we were trying to show here actually is that most or all of the moly was coming out as the moly sulfide. That we didn't have lower activity because we had a nickel moly phosphide phase. We really have predominantly a nickel phosphide phase. Okay, and finally, if we look at the last one, this is the moly edge, and the moly edge seems to correspond to MOS2, as in the reference spectra. And so I think to a very larger but true approximation, these phases have separated from each other and we do have this co-mixed but closely associated MOS2 on the nickel hydroxyphosphite. Okay, so let me go on then to the conclusions. So we prepared hydroxy. I see we got a little error here. The nickel hydroxyphosphite precursors were hydrothermally prepared. The moly is incorporated during the synthesis, and it increases the surface area. During sulfidation, we get dispersed islands of MOS2 segregated from the precursor, and these islands dissociate hydrogen and promote reduction of the phosphite precursor to nickel phosphide at lower temperature than in the absence of the moly. And the diesel HDS activity correlates quite nicely with the nickel phosphide surface area. And to be competitive with state-of-the-art catalysts, we're going to need to have these crystallites about the size of 30 angstroms. So finally then, on my last slide, I have some take-home messages. So here's my recommendations for those of you that are also working in the area and would really like to help. What we need to do to understand this system further, I have two approaches. One is proof of principle experiments. For proof of principle experiments, we can say, yes, use any method that you would like to make smaller Ni2P particles. Use nanomethods, but get that size down to the nanometer size, and let's see whether there's any structure sensitivity as we go smaller, or if we're really stuck with getting things in the size that we want. Okay, next. So but then there's a second one, which is to move towards practical applicability, which is what's talked about in all the papers that you read on this. There's more steps that need to be done there. We need to do the same type of experiments, but we also need to find a way of making these things at that size in a scalable, simple, environmentally benign method. And that translates largely to exclude high boiling organic nanomethods where you boil things at 350 C in organic, use of phosphine, and even the elimination of noble metals. So there's a challenge ahead. I think there's room to play here. And of course, it would be preferable if you could do it if you could do this in the presence of sulfiding agents, although that's not a criticality. So that's kind of the take-home message I have. I think we're a distance away from where we need to be to move these things into sort of the real world. There's some steps that still need to be taken in proof of principle to see whether we could actually get there. And I know that some of the workers are working on it. The last papers, as I've said, I've seen that struggling with maintaining the nanoparticle size that they create in a very sophisticated way. And so there's a lot of work yet to be done if we're going to actually move these. So that is pretty much what I wanted to say. Finally, on the last slide, I just want to thank my coworkers from ExxonMobil that I already mentioned, Trudy Boland from Argonne, and ExxonMobil for allowing me to talk about this and coming to this fun meeting. I told them I wasn't going to go to the horse races or drink the bourbon or sample the tobacco. So they said, okay, you can come. And thank you for your attention, and I'll try to answer any questions if I can. Bruce. It was similar to the cobalt moly sulfide. Okay, I'm sorry. Okay, so in doing HDS reactions, there's always a question on the type, whether it's a direct reaction or whether you do a hydrogenation first. And that's kind of the question that Bruce, and that's relevant to how it reacts with hindered dibenzothiophenes or not. So the comment to that question was, yeah, they behave very much like cobalt moly. There was nothing spectacularly different about that on a selectivity basis. Bruce.
So, Stu, did you rule out MOS2 as a real catalyst?
Okay, not 100%, except for the following respect. The first catalyst that we had in there had no MOS2 in it, and it had 15 meters squared per gram, and it lied on the line. Okay? I think what's still necessary here, we want to get some XPS and just at least show that that we don't have any nickel on the MOS2. I would be more worried about that than just MOS2 by itself, because that's really, really low activity, and we have a very small amount. So yeah, that's what happens when you have a mixed catalyst. It's a little tough to absolutely do that, but I'm pretty certain from that correlation that we don't.
There is only one more question. Excuse over there.
You mentioned, you showed that when you added Moly and cobalt, you were able to change the surface area. Do you have any insight as to why adding liquid metal changes the carbon size?
No, no, not exactly. That's, you know, that's sort of the serendipitous nature of sometimes making things. Why the Moly? You know, you could think that the Moly is disordering the material a bit just because it's not exactly the same size as the phosphite, and sometimes that creates strain, and it does intercepts the crystal growth as the things form. That's about the best hand waving I can do on that. Yeah, be around at the coffee break.